Perfect. I think we're good now.
Okay.
I'm going to send it over to you.
Okay, very well.
Okay, make host. Okay, awesome. Go ahead.
Okay, perfect. So maybe a couple more minutes, so 2 more minutes. So briefly about myself. So I just put my LinkedIn and Twitter. If you want to connect, feel free. I'd be glad to connect. Briefly about me, I did my PhD in engineering. I did. I was doing machine learning, but not the deep learning machine learning. It just the traditional machine learning, decision trees, and all that. Building healthcare applications. After that, I was faculty teaching engineering, and then moved to industry. Works at different startups and all. If you are, and then right now, and after working at different startups in computer vision and others, NLP, now I'm at NVIDIA as a deep learning instructor. If you are on the path or this sounds something you're pursuing, feel free to connect and ask me anything. Okay, so maybe another minute or two for everyone to join in, and then we'll start talking about CNNs. So again, what we'll do, the plan is we'll do this today and next week. So what happened is CNNs, they were proposed in the 90s, and then they fell out of fashion because they weren't performing as well as other machine learning algorithms in computer vision. And then, of course, they came back after ImageNet, 2012. So what we'll be doing today, we're going to be living in the 90s, and next, but it's very important because there is pretty much the whole lecture is about, well, it's not a lecture, it's a study group, right? And I even have the book here open, so if we need to reference to anything. But what I was saying, the convolution, that trick is that what we want to mainly understand today. So the goal by the end of this session, we all want to just, okay, when we see a CNN, when we see a network like this, we know all what's going on here. If you already see it and if, for example, this step here, oh, okay, this is a convolution and this is a kernel of size 4 and all that, maybe just sit back and maybe you get to answer some of the questions on Slack or but the goal eventually is we are all comfortable building, looking at this, knowing what's happening between every layer. So we're going to talk about the different layers. We want to understand what's happening between every layer, because this is the base. Because everything that we'll do, for example, so we're going to see at the end of today, we'll see like Lynette, which is the first proposed CNN back in the 90s, but everything really builds up on that. So if we really understand this one, what comes next, for example, next week, the next chapter, I believe it's modern CNN. So there is AlexNet and there is Inception there, I'm sure, maybe ResNet and all those. And really everything builds on this. Everything actually builds on the architectures before it, but really everything builds on this. So I think 6:07. So I think we can go ahead and start. For the questions, I'm gonna pause here and there, and I'm so glad that Elvis is also here. So you can probably post your questions on the chat. Maybe Elvis can answer. If Elvis wanna, maybe during the pause, wanna just ask me those, I can answer those, but we'll work it out. Okay, so starting. So next time, I'm gonna mention the different applications where CNNs are used. Really, the applications are limitless. You can think from self-driving to facial emotion recognition, to working with maps, to so many applications. But if we were to summarize, maybe like the key ones, like we have these classifications, and the common one is cats and dogs, right? And that's the traditional, the first one. And then there is segmentation, and you can see here, segmentation is when we're going after segmentation. It's also based on, so all these are based on CNNs. And then there are others, okay. And then there are others, like nerve style transfer and so forth. And we'll dig more into this when we talk about the different architectures. Okay, cool. So now let's understand why CNN. Why not? So I believe you've already talked about MLP. So right now everyone is familiar with the multi-layer perceptron. So why not just really process images with just a multi-layer perceptron, right? So with that, I'm going to ask you this question. But before, I had this slide which I already covered. So, and I wanted to present this slide at the beginning. Now we're going to look at it at the end, but maybe now you look at it and you say, oh, okay, well, I don't know what's going on exactly between here and here. But me being a good mate, I have to make sure that by the end of this, you will certainly understand all the steps here. So I believe you already, for example, here we have the fully connected layers. So I believe if we take the left side parts, I believe here you're already fine. But now today we're just adding CNN. Okay, so we'll start with this question, right? Why not just use multi-layer perceptrons with images? And with that, let's think of a scenario. Think we have a 1 megapixel image. And so one megapixel image, and we have one hidden layer. So if I was planning on using my notepad, but I didn't want any glitches, so I said I'll pass. But if you do have a pen or something, I think here and there I may say things, and I think it's great if you have a pen next to you and you can like draw it down. So for example here, how about you draw 1 megapixel RGB image, and then here 1 megapixel, so it's 1,000 by 1,000, and RGB, there's 3 channels, so it's kind of like draw like 1,000 by 1,000, like 3 kind of like the cubes behind themselves. So that, and next to it here to the right, you have a hidden layer, and the hidden layer has 1,000 units. Okay, so if we're wondering what's the weight matrix if we use a fully connected layer. Again, what's a fully connected layer? Meaning every node in those 1,000 is connected to all of the 1,000 by 1,000 times the 3 channels. So 1,000 times 1,000, a million times 3, so 3 million per node. Excuse me. So per node, so that's like right, 3 million times 1,000, so that's like 3 billion. So the weight matrix would have 3 billion parameters, and we don't really want that. We don't want that for many reasons. We don't want that, for example, if you have all those parameters, first of all, you need a huge data set, right? You need a huge data set to even train, because the number of parameters is so big. Second, you need so much compute if you have all those parameters. You're most likely to overfit as well. Anyway, so this is the key. So we're trying to kind of minimize all those. Now the 3 billion, if we use the convolution, it's going to be a lot less. And now we will see how is it going to be a lot less. So that's the key. So the key that we want to use high resolution images, even more than this 1 megapixel image. and this is just one image. So now imagine if you have a data set that you have many images so there's going to be a lot more. Okay, so that's why we use this convolution. So let's understand what is this convolution. And with that, so I'm trying to follow the format of the book. There are different ways how anybody would like present the CNNs, but since this is a study group about this book, and I personally like the book for many reasons. One of the main reasons is the book is actually updated all the time, and not a lot of books are like that. So that's I think great about the book. So yeah, so the format here and all that you see is from the book. So that way you can even ask specific questions about paragraphs, and maybe you have any questions on. I made sure I read the chapters. So so what is the intuition? Okay, so now we know the limitation, the constraints of fully connected layer. What is the intuition behind CNNs? And we'll get to the convolution in a second. And the book, they give this "Where is Waldo" example game. And then they talk about translation invariance and locality. And so here, if we take this picture and we say, where is Waldo? Okay, I was pointing with the mouse to where is Waldo, but if you look at it, okay, Waldo is here. But really, Waldo, what translation invariance is, Waldo doesn't really change if he's here or really here or at some other point. And that's what translation invariance is. So meaning that our network should really act or handle Waldo the same in a way, if no matter where he is in the image. So that's pretty much the example that they give. And locality, we don't need, for example, these people here on the boat, they don't really provide much information for us to know much about Waldo. So what that means is we just need the pixels around Waldo. So maybe we just need a few pixels here, and those can tell us, and then like we can slide, and those would tell us, oh, okay, is this patch Waldo? Is this patch Waldo? No. And that's locality. And so these are the intuitions behind CNN. Okay, so let's delve more into them. I was not planning on presenting math at the beginning of the lecture because I know that may throw some of you off, but there is really no reason to be thrown off on this one. So this is again the equations that were shared in the book, but yeah, let's go through it. So here. Now, okay, I said an MLP recap because you've already covered MLP. So consider an MLP with a 2D image, X. So X is indexed K and L. And there is a hidden representation H, that's also it's in 2D. Again, now if you have a pen and paper, it would be really great to maybe draw some. And by the way, I may be going slow. Maybe there are some of you that they're already very familiar with this, but I'm taking no assumptions. Maybe some of you are just getting through this. So if you already know all this, you know, just bear with us. It's going to get more advanced as we go. So we have X. So we're going to draw X. It has indices K and L, and then also our H is in 2D. So we're going to draw here on the right our H as in 2D, and the indices for H are I and J. So now, what is the weight matrix between these two? Using MLP. Again, MLP, it's a fully connected layer, meaning every feature in our hidden representation is connected to all the input features, okay? And this is exactly why we have this weight matrix labeled by all these 4 indices, I, J, and KL, okay? And it should be good if you can actually draw the lines between them. And actually, maybe next time I can just try it out on the notepad and then share that with you. If you guys all got it, that's fine. So yeah, so that's pretty much it. And so this is the MLP. So this is something that you've already seen. So nothing new here. This is just a bias that we add. And then here, if we say, if we re-index, this is just re-indexing. We're gonna say K is I plus A, and L is J plus B. So we just replace that. And same thing here. Here what we did, because we just replaced that here, because this is just a weight matrix, we can just simply change it with another matrix. And this is what we did here. And here we said that this new matrix V is just same as this one. So this is the one. Let's see. Yeah. This is the one that we had. So I think this is clear. If you have any questions about this, please let me know. I'd be glad to revisit this one. Okay, so here, based on multi-layer perceptron, we have our input, we have the weight matrix, and this is our hidden representation. We add some bias here. Okay, next, so now we're gonna talk about those two intuitions. So how are we gonna use those intuitions to really, from this equation, we're gonna derive now the new equation after convolution. Okay, so now we're gonna go from a multi-layer perceptron, something that we already know. So here, I believe we are all familiar with this one. And now we're just gonna add these two intuitions on top of this one. So what was the first one? The first one was translation invariance. What's translation invariance? Again, we said Waldo doesn't really matter if he's here or anywhere, right? So a shift in Waldo, a shift in our input should simply lead to a shift on the hidden representation. Okay, what does that really mean? That means that our weight matrix should not depend on I and J of the hidden representation. Okay, and I'll just pause there. So now if going back to, if you draw those two next to each other, I and J in the representation, our weight matrix should not depend on the location of Aldo. So with this one here, we can really just take off this I and J from here. And then with that, we're just gonna be left with A and B. Okay, and you know what? I'm gonna open the chat, and in the chat, if you feel like, hey, maybe explain that more, please. Okay, cool, awesome. Okay, so this is what translation invariance is. Okay, so now, and this is very important. Why this is very important? Because here now, if you already drew this, you had all the nodes on the hidden representation connected to all of the input the input features. But now we're not gonna have that anymore. We're actually gonna just have them linked to only specific patches. Let's just say patches, okay? Maybe I can draw this next time. But okay, so far we're here. And so these two, so the weight metrics and this one, they do not depend on I and J. Okay, so now this is our new equation. And this is really what convolution is. So this whole operation here is convolution. And we're gonna see more in details what is convolution. And again, the book says that this is actually cross correlation and not convolution, which is exactly true. And we will compare between what is the difference between convolution and cross correlation. And okay, I'm not gonna look at the chat, so maybe not to get too distracted. Okay, are you referring to the output of the layer that we pass on to the next layer? Why does V have 4 indices? Okay, so V have 4 indices going back because from this one, okay? V have 4 indices because we're really all that we did we really replace this matrix here with just a different matrix. So here there is not much, nothing changed. And if we because it's a multi-layer perceptron, we have 4 indices. It doesn't depend on INJ, so with this we can just take off INJ. I'm gonna keep going, and then in a bit I'm gonna pause and take all the questions. Okay, so now we have this. Okay, cool. Locality. So what's locality? Locality, again, we said that the Waldo here does not depend on what's happening here far away. So we can only really look at the pixels really close to his face, to what really represents Aldo. And that's exactly what this one, what locality is. And then we add this delta, which we can think of as a threshold that we say, you know what, we're just going to look at between only here and here. And we're only going to look at between here and here and so forth. So anything outside, so pretty much going back to the metrics, anything outside these pixels, it's going to be 0, okay? So we kept everything the same. So this is the equation that we got from the previous slide. Nothing added, except now we're actually making our A within a threshold. And that threshold is what we call our kernel. And I'm gonna, and it's no worries, if you are lost at any point, I will go back and I will even draw that. So it's fine. If it's fine, if all these few equations didn't, we can go through the book and I will revisit them again. It's no worries. But this is the key here. Okay, so I'm just explaining what translation, invariance, and locality are. Okay. Okay. So with that, what is this cross correlation, which is also called convolution? And this is the part that everyone. Okay. So now maybe if you're lost, okay, now I hope you're not. But now this is what cross correlation is. So you have this kernel, and this kernel comes from this threshold that this is how we're relating the equations with this kernel. So all that we do is we multiply and sum. So for example here, so say we have this kernel. This is our input. You can think of it as an image. Okay, so it's like a 2D. It's a 2D tensor. You've been dealing now with tensors already. So this is like a 2D tensor or a matrix. We overlay this one here. It's like we multiply and then we sum them up. So if we, and this is here, you can see 0 times 0, 1 times 1, 2 times 3, 3 times 4. Right? If we add them up, we're going to get 19. Okay, now what we do, we slide exactly as you see here, we slide that window to the right, and then we get the 25. So now if we slide it to the right, we're just going to get that kernel times what now? Times 1, 2, and 4, and 5. And then we'll get 25. And then after that one here, it goes down here. So if you just want to code that, it's like one for loop that's going over the columns and another for loop that goes down the rows. Okay? That's pretty much what cross correlation is. And this is really what convolution is. Okay? So a convolutional layer, so now that's what cross correlation. A convolutional layer is simply the cross correlation plus the bias. So we do our cross correlation, we get that's what we just seen on the previous slide. And then when we add the bias to it, that gives us the output. And this is what we call a convolutional layer. Okay. And instead of doing, I'm gonna try this this way now to kind of even instead of trying the code later, I'm gonna just try the code now, like throughout how we go, and then okay. So let's jump to the code. Okay, so we get this all of us. So well, all that we did, we just multiplied and we got that. Okay, cool. So how the book did that, let's go and see. Okay. Or what I can do, we can actually have them. So we can actually have them next to each other. So that way we can, okay. So this is what we talk. So, okay, so let's implement this one. Let's implement this one. So cross correlation, okay, so I guess we'll go back to the cross correlation. So cross correlation again is just two for loops, right? One going through the columns and then the other one going through the rows. And that's exactly what the code here is doing. So to compute the cross correlation, let me maybe zoom in there. So to compute the cross correlation, we have our kernel. So this is what we could, so this is the kernel. Again, from the threshold, we get this kernel. We have this kernel that has a shape, height and width. And then we have our output. Something here that I didn't mention. What's the size, what's the shape of our output? It's the input minus the kernel size plus 1. Okay, input, for example, let's say, for example, here, what's our input? It's 3 by 3, right? So the height NH would be 3, and NW would be 3. Minus, again, here they're the same, the height and the width, so 2, 2. So 3 minus 2 plus 1, that would give us 2, 2, okay? Okay, and so we specify the size of our y here, and pretty much we just multiply them. We just multiply them, and then we just sum them. Okay, and then this same exact example, the 0, 1, 2, 3, 4, 5. Here we can just do it as a 2D tensor here. So we have just a 2D tensor. And we do cross correlation with this kernel here, same one. And we get the same result. Okay, so I think that that's clear. Okay, so for the convolutional layer, okay, yeah, actually, let me do this. I think that's good.
Hey, Salim.
Yeah.
Are you sharing two screens, or because we can only see one screen, but it's very, very small.
Oh, I'm sharing two screens. Oh, okay.
We're only able to see the slides, but we're not able to see anything else. But it's very, very small.
How about now?
Yeah, now we're able to see. Yeah.
Oh, okay. Thank you for that. Yeah. And you know, Elvis, even for the questions, if anybody, if somebody says I'm very, very lost, then please interrupt me and tell me. If it's, you know, like I don't want to keep going, and you know, so we want to make sure that yes, we keep going, but we want to like take the questions as well. Anyway, so okay, so thanks for that. So all I was saying is I had these two pulled up next to each other. Now I believe you can see both screens, and I was just talking about what we just did here, or what we just did here, how like, okay, we're computing the cross correlation, and then we have our kernel shape, the height, and then we declare our y. The shape of y is just that. And this is exactly what we see here. Here, the x shape minus h plus 1. Okay. And then a for loop going through the columns and a for loop going through the rows. And then here we just multiply. We just multiply and then sum. And then that gives us our y. Okay. And then this is the same exact example that the book presented here that we have here. They just do it here. And then you can see that the result is the same. Okay. So we'll run that. And okay. So that was cross correlation. So for the convolutional layer, is just the same. What did we say? It's just the same, but we just add the bias to it, and that's all that we do here. So we define this function, which is pretty much just our cross correlation plus our bias. And we define these two parameters here, the width and bias. And again, all this is from the book. And let's do the example of the book of the edge detection. I have another example that I like that I will present in a few slides, but let's do the example of the book here. They initialize this tensor with all ones. So they're all ones, and then they go, and between 2 and 6, they put zeros, okay. And then they say, and then now we have this kernel. What's the size of this kernel? It's 1 by 2. So what's this kernel? So here we can think of 1 as being white and 0 as being black. What we're trying to do, we're trying to detect the edges. So all that we're trying to do is where does this really change? So what we're trying to do, this kernel is trying to detect our vertical edges. Is there a vertical edge here between here and here? No color change. So now there's nothing. Oh yes, there is a color change. Okay, so we were expecting there to detect something. Is there a color change here? No, and so forth. Okay. And so if we now apply the same cross correlation between this K and that, that's exactly what we get. We get the 1 here, meaning that there was edge detection between 1 and 0, meaning going from white to black. And then when we get the -1 here, that means we detected change and edge detection from black to white. Okay. So that's all what that is. And then I think they say a question in the book, I believe they say, if we do the transpose, and then can this detect horizontal, and then can this detect horizontal edges, and this one would not detect horizontal edges. If we want to detect horizontal edges, we want to change the kernel to really be just that. Okay. Okay. Okay, so with that, talking about now, so the key here, all about deep learning, what we try to do, we try to learn the weight metrics. That's all what we visited, the backpropagation and all that. It's all about finding those weights. So, and this is what they present here is, okay, now say that we have an input, and then say that we have an output Y. How do we go about finding the kernel? Okay, and then here we already know the kernel size. Okay, so we already know kernel is 1 by 2. How do we go about finding the weights of that kernel? And this is where the backpropagation comes, right? So, and that's what we have here. So we have this 10 iterations that we're going to go over, and then we do the convolution, the 2D convolution of X that gives us our prediction, Y hat. Again, this function that's just conv2D, we get this prediction. And then this is our loss, right? This is just the squared error between the prediction and the actual output. And then here we zero the gradients before we do the backpropagation. And then we just update the weights, and then we just iterate through that 10 times. That's all that we're doing here. And then by the end of this should really have the weights of our kernel. Okay, let me zoom out. Let's see, it's the error there. Okay, the error, shape is invalid for, oh, okay. let's see. Okay, this should be fine. Okay, let's see now. Okay. So yeah, so and then this is what we got, 0.98 and -1, which is very similar to that kernel that we actually had at the beginning. So just straightforward. So I believe since you've already maybe went through the first chapter, so nothing here. So very similar to the multi-layer perceptron, how you would find those weights. Okay. Actually, I think this is a good part, a good point to make a pause and then take questions now. Actually, the next point here. Okay, so now I'm gonna just go to this window only. So I'm gonna go now to my presentation slides. Okay, let me just go there. So yeah, yeah, this is a good point to, I'm gonna pause and take any questions and then we keep going. Let's see. Okay, that's okay. So I'll see. I'm looking at the chat right now. So okay, so okay.
So there's a question there, Salim.
Yeah. Yes.
About the weight matrix. So the question is, if the weight matrix is directly replaced with a kernel in the convolution layer.
Is the weight metrics so okay? So that's a good question. So usually, for example, when we start training, like if you remember with the weight matrices, we always start with like random weights, right? And then over time, we update those weights. So it's very similar to the kernel. So eventually, yes, you have the size of your kernel, wherever that is, 3 by 3, 5 by 5, and all that you're working on is you're actually updating. Oh, well, so you have the kernel. So yeah, so that's what you're learning. So you're learning the kernel, the kernel weights, the weight metrics. Okay, yeah, so I hope I didn't confuse you there, but yeah, what I said, so yeah, so you already know your kernel, and then with the back propagation, you just try to find what is the different, every kernel, you can think of it that it's extracting a specific feature, for example, and then we'll see later, we'll talk about channels, but that's how you can think of it. Okay. What are some other questions, Elvis?
Cool, that's a good explanation. And I think someone mentioned it in the chat as well. So I think that's pretty consistent.
Okay.
Another question here. So the question is, by doing the convolution, aren't we reducing the size of the image?
Yes, exactly. That's a very good point, and that's why we have padding. And exactly, and we'll get to that. Right. That's a very good point, and that's we'll get to that. Yes.
And also a question, I think maybe later on you can answer, but if you have time, maybe. So the initialization is the same as in a normal neural network, like Xavier initialization? Or
so
maybe...
we'll talk. So right now, let's not worry about the initialization. Right now, you can, for example, if you used whatever initialization you used right now, it's fine. So if you use Xavier, for example, or it's fine. So for example, at the end, when we'll get to the limit, we will see, for example, which initialization we'll do. And so for now, it's fine. Just think as you have a random initialization right now.
Okay, one more question. I think this is a good question. Is there is, I don't know if it's a question or a comment, but I think the question is there a way to define a kernel size just using the input data?
Just using okay, so with that there are like good practices, standards, let's say. So for example, there are very common kernel sizes already. So for example, you'd find people usually using like a 3x3, a very common one, or a 5x5, or even a 7x7. So these are the most the common ones, but getting a kernel size from the data, no, I mean, again, this is this is a good point. So here's the thing. I'm sure you guys have talked about hyperparameters and parameters. What's the difference between hyperparameters and parameters? So the hyperparameters are things that we set, right? So you can think of your question that you asked me. What's the size of my kernels? What's the size of my kernel? It's a hyperparameter, so it is up to you. And then anything that's up to you, people have experimented with it. What's the best one? And same thing with that. Anything that comes to your mind as a hyperparameter, from the learning rate to a kernel size to anything. So, and best practices: 5x5, 3x3, 7x7, and then we'll even talk about why odd, why not even. Elvis, any other question?
I think we're good now.
Okay, perfect.
Thanks.
Okay, yeah, of course. Okay, awesome. So what's the difference between cross-correlation and convolution? They are pretty much the same. Just the kernel is flipped in convolution. And this is what we see here. So A, B, negative A, and negative B. And then here, when we say the kernel is flipped, it is flipped horizontally, and it's also flipped vertically. That's all the difference. And then, so if the kernel is symmetric, the result will be identical. And then here I have an example. So for example, and I took these screenshots, I think from scanned book or something there I saw, but they make the point. So say you have, this is your input, and this is your kernel, okay? And you see how here, like there's W. So think of you will find it's being called kernel, filter. These are the two common ones. And we'll see even later what's really even the difference between a filter and a kernel. But anyway, so we have this. And this is, if we do our cross correlation, this is what we get. And I'm gonna pause here. By now, you should be able to get this, of course, by yourself. And then if we do a full convolution, we're not gonna get this, we get this. Okay, that should make sense. And you can just, if you just get how you made the 9 here, you got it, right? Because like you start here, so this is a 3x3. So you start here 3x3, and then you slide, you slide one stride or one thing to the right, and then one to the bottom. And then so here you'll get all zeros, and then you slide and so forth. And then once you get here, what's the first one that you get? It's when all the 3 here and 3 here. So what the width, so I'm talking about this. So which one will touch that one first? It's gonna be the 9. And that's why the 9 is here, and so forth. If you actually flip what we said, convolution is just the kernel flipped horizontally and vertically. So if we flip it, actually 1, 2, 3 will be flipped. It's going to be 3, 2, 1, and also vertically. So it will actually end up something like that. Okay. So this is actually what's going to be your kernel, and if you do it, and this is what you will get. This is the result for convolution. Okay, that's all. So they're the same. So actually I took this from from this book that I have, and I was reading it, and this is fun. But so I took it from this book. If I don't see myself, but I took it from this book, and he says that many machine learning libraries, they implement cross correlation, but they call it convolution. But does it really matter? It doesn't really matter. Why? Because what we're trying to learn the kernel, right? The kernel. That's what we're and that's what we're focused on. So it doesn't really matter. But and go and do some research. You'll find some, you know, here and there. But just know that the core of it is cross correlation. Okay, there is this cool. If you are if you've watched Fast AI, and by the way, I was actually I would do a shout out to all the Fast AI fellows because um, because when I first moved to San Francisco, actually the first thing that I joined was here at USF. Jeremy and all the Fast AI fellows were here. So anyways, my point is he likes to show this one, and I also really like it because it makes a point of edge detection, but just like what we saw, but even more. So here what we have, so we have an image. So we have an image, and then you have the pixels of the image here, okay? So, and then you have, this is the kernel that we've seen. So far, we've been just looking at this 2 by 2, right? So far, we've been looking at this really 2 by 2. Here, the only difference is it's a 3 by 3 kernel, okay? And then all that we do is we multiply this kernel with you see this red things. And then what we get as the result, we get edge detection. And that's all what's going on. And so this is how edge detection, for example, happens in images. So we just related what we just seen on these numbers now to actually an application. Back in the day, edge detection was not done this way. Back in the day, edge detection was done differently. But yeah, so here you can, and I've shared that, you can come here and play with it. So what we're here, if you notice, when we change this, it just changes our kernel. And by the change of our kernel, then our multiplication with this image is just gonna give us different things. So we see, for example, how this lift Sobel. So here, there isn't much difference between the colors, right? So there isn't, but for example, when we go close to the eyes, we find there is the edge detection. And where's that coming from? That's really just coming from the kernel. Okay. And you can see that this is kind of like a symmetric kernel. This is kind of how it's really this one, an edge detection kernel, because it's kind of like 1, 2, 1, -1, -2, -1. Okay, so this is really cool. So just go and play around with it. And also, there is a second example here for it, where you can actually play around with changing even the values of your kernel. You can give it any kernel values. Okay, cool. So I think this, because it's always good to relate what we learn the theory to application. So I think this is good. So moving forward. Okay, I'm gonna do another pause. I'm gonna do another pause for questions after a few slides. So far we've been talking only about a single input channel, but in reality we asked that question at the beginning, RGB. So RGB, it's not a single channel. It's, so for example, when we're talking about grayscale, it's one single channel, but RGB is 3 channels, right? So we want to be able to deal with multiple input channels as well as multiple output channels. Okay, and this is what we have here. But really, with the cross correlation that we understood, really that's the core of it. So nothing changes. So here, okay, we added a channel. Here, a point that to make, and I noticed here, the kernel must have the same number of channels as the input. Okay, so the channels in the kernel, and why? So that way we can do our cross correlation. So this first channel of the kernel is going to go with our first channel here, and then the second channel of the kernel is going to go with the second channel of our input. We do our multiplication, and then we just sum the whole thing, and that gives us here a single output channel. A single output channel here. Okay, so really nothing changed here. you can look at this one, you can say, oh, okay, I can multiply this and I sum them and I will get a 2 by 2, and then here I will get 2 by 2, and then I can sum them. That's fine. Or if you sum them, it's just the same, really. Okay. Okay, so there was a single output channel. How about multiple output channels? And this is, so now, for example, here we have this colored image. So it's an RGB image. So we can think of it as a 3-channel image. And we went from this, we did convolutions, and forget about all this. Let's just focus on just this one here and this here. So we have this input with multiple channels, with 3 channels, and then here we have multiple output channels. Okay, the only difference between what we've seen here and then what we've seen here on this one, this is the difference. If we take this one and we say, let's add another kernel, we're gonna add another kernel, which we can now call a filter. Okay, so we can still say we have one kernel, but this one kernel have 2 filters. Okay, so with this one, and maybe same as this one, but maybe just different values here. And that's going to give us what? That's going to give us this one, and it's going to give us another channel. And if we have maybe 3 filters, maybe if we have 4 filters, for example, so here we have 4, so we definitely had a kernel with 4 filters. The 4, because we have 4 filters in our kernel here, we're going to get 4 output channels. And that's all that there is. So now, perfect. Now we understand this. Now when we look at, we see this, we know, oh, okay, we just used 4. Okay, there are 4. These we call them feature maps. Oh, there are 4 feature maps, meaning we used 4 filters. Our kernel had 4 filters. And I'll pause there, and you see how we said feature map. You see a feature map, and the feature map really corresponds to like, so this is one feature map. We can think of it. We can think as here we have 4 feature maps. Meaning what? Meaning every feature map is corresponding to a filter. Okay, good. Meaning what? Meaning that filter is maybe detecting something. So maybe one filter will detect the edges, the horizontal edges. Maybe another filter will detect the vertical edges. Maybe another, and so forth. And this is in the lower levels. And you can think the more deeper you get, then that's how, for example, let's say a face is detected, because there were filters that maybe they were detecting something specific, maybe the eyes eventually on a much higher level, and so forth. Okay. So now, okay, we are at least fine. We have this input, and then when we look at this, okay, we just say, okay, we know how we got here. We had like 3 channels inputs here, but now here we actually have 4 output channels. How did we get 4 output channels? Oh, because our kernel had 4 filters. Oh, okay, that's fine. But then if I ask you, okay, the kernel had 4 filters, but how many channels did every filter have? Oh, you'll say, well, that will depend on how many channels were on my input. Oh, your input was an RGB image. It's 3 channels. Okay, so every filter had 3 channels. Okay, so we had 4 filters, and every filter had 3 channels within it. Okay, cool. You see, for example, here, because here we only had 2 channels. Okay, I believe that should be clear. The last point here to make, this is just like a special case of this multiple output channel. This is just a 1-by-1 convolutional layer. And you may even say, when would this really be used? But it is used. And there is a very popular architecture called Inception, which I believe it should be. I didn't fully go through the modern convolution, but it should be. I'm expecting it should be on that chapter. And one component of it uses the 1-by-1 convolution. And so when do we really use this? So, okay. So for example, here, I'm going to step back just based on what we learned. What do we have here? Oh, okay. We have an input that has 3 channels. So our kernel must have 3 channels. Okay, perfect. But how many filters do we have? We have 2 filters. Okay, we have 2 filters, meaning what? Meaning we're going to get 2 channels out, and that's what we have here. We get 2 channels out. And then we do the cross correlation between the kernel and what? Between our kernel, and then we slide it. Here, we just slide one by, because there's just one. So we're just going to get the same size. So, and this is how this one by one is used. So we actually, the input size does not change, but what really change is the number of channels. Oh, how does that change? Based on how many filters we have on our kernel. Okay, so if you, and this is how I also noted here. So when do we use this one by one convolution layer is to adjust the number of channels between the network layers and to control the model complexity, okay? So you can think of it now, again, as we said, this whole filter maybe is detecting something, this is detecting something, and then you got this, maybe now you can go from here now, and then you can go to maybe a single output channel and so forth. Okay, but I believe so far so clear. We're gonna go through the code, and after the code, we'll take questions. Okay, let's do the double screen like earlier. Okay, let's see. Oh yeah, 1 second. Elvis, while I'm doing this, please ask me if there is anything, any questions. Okay.
So far, so good.
Okay, thanks. Okay, let's have now these two next to each other, and then we'll run the code. Okay, so we're gonna run here, we're gonna run the multiple input channels, we're gonna run the multiple output channels, and the one by one. Okay, so let's go back to that multiple one. Okay, okay, so we've already done the cross correlation, so that's good. So here what we have, okay, we define this. There is nothing here that changed. This is our cross correlation. And then here we just use this zip. We just zips our input with our kernel. You know, if you're not familiar with this one, you can just do it by itself, and then see, for example, and then see what you get. So for example, I'll have to do it if I want to do it. I'll do it after this one. So if we zip that, you can see that it took, so for example here, it took the first one, the first tensor, it zips it with this one, and then it would take the second tensor here, and it would just zip it with this one. Okay, and then it's pretty much just performs the cross correlation on them, just as before. Before we only saw a single example, right? A single one. Now it just both, and it just adds them. So it just sums everything. So there is really nothing here new. It just now sums everything together, and that's how we got here our 56, 72, 104, and 121. Okay. Okay. So for the multiple output channels, yeah, what we do is we just stack the results together. So here, the multiple output channels. So what we're going to do is we're going to use this example that we have here. We're going to use this same one here. What did we say now? If we want to have multiple output channels, we just want to have more filters, right? So we just gotta have, we still want to have like a 2D, two channels in, but more, okay? And this is what we do here. So for example, here we take our kernel and then we add +1 to it, and then we add +2 to it. Actually, so this one, there is something called broadcasting. You've probably seen it already. So all that it does is broadcast this +1. It adds that to the whole kernel. So actually, for example, so here, what we will do. So actually, yeah, we can actually and you know, you can just. So this is our first one, 0, 1, 2, 3, 1, 2, 3, 4, and then it just adds 1. So it just adds 1. Now we have, this is our second filter, and this is our third filter. And then we just, do our regular cross correlation. Okay. And then we get 3 output channels, 1, 2, and 3. So now this is the multiple output channels. And then the last one, this one, the convolutional layer, was just a special case of a multiple output output layer. And here what they're doing, pretty much with the book they said, they related this to really using a fully connected layer, which is the same. So and this is how they, so if you, so you see like this is a new function that's pretty much that it just uses the matrix multiplication, the dot products pretty much. And then they show how doing it this way is just the same as, you see, this is the new function that they did. And they show that doing it this way is the same as if we do it our other way. You see how here, like, for example, when you subtract them from each other, the results would be smaller than this. That's true. And if you would like to think, how is that? Here, what they did is they reshaped them. So you can think of this. Okay, so maybe this is like a homework or not a homework, just a practice kind of thing. So how about if you have any doubts here, what I would personally suggest, how about you draw this and see how they reshape this into, for example, if you look at here, it's going to be, and what happens here, K. So what kind of matrix multiplication is here, for example, for this example? It's going to be here 2 by 3. K is going to be now 2. Here you see, if we reshape it, it's going to be 2 by 3, which is just these 2. And then our X is going to be, when we reshape it, it's going to be 3 by 9. Okay, now we can actually do matrix multiplication 2 by 3 times 3 by 9. And that's going to give us 2, which is 2 for the output channels, and 9. And then we're going to have to reshape exactly. And that's what they do here, the reshape and 9 again. So it's actually, so it's actually the height and width, 3 and 3. Okay. So that'll do it for now. And moving on, we're just going to do some more recap, or we're going to go even more practical now. So I'll pause here and we'll take any questions, or yeah. If not, we'll keep going. Okay, cool. So now you should be seeing, okay, yes, now you should only be seeing this one. Okay, so far, so good, right? So, okay, so now let's put everything together, what we've learned so far. Oh, okay, Yes, I thought those screenshots. Okay, so we have the fully connected layer. For example, here, if we have our input as 1 by the 3000, we have our weight matrix, and then we get a number from the dot. If we just do the dot product, we're gonna get 10 outputs here, right? Okay. This is just using the fully connected layer, so nothing new here. Now let's just take this and do it now in 3D, right? For example. Okay, so now we went just from this one. So this is something that you probably implemented on the last chapters. Now we're gonna go into 3D. So now, for example, we have a 32 by 32 image, and then we have 3 because it's a color, and that's why red, green, blue. So it's an RGB. And I have to actually to give credit for where I got this slide from. So I got them from Justin, I believe his name, Justin Johnson. He was the one, I believe he was the one of the TAs who taught the Stanford Convolution. But I will actually post a link here. But that's where I got this. I really like the visualizations here because they make the point. So we talked about the filters, right? So now we have this filter that is, this is a single filter that it has a size 5 by 5 by 3, okay? Why the 3? Because it has to match the input channels, okay? And now when we convolve it, it's just kind of, we like overlay it, and then we just slide it all over, okay? And then you can do the math and then know what's the output. So if you remember actually from that equation that we saw, what's the output that we're expecting? If you remember, if we have an input image and then we have a kernel size, we can predict, we can say that's the output. So the output, we say it's the input minus the kernel plus 1. So for example, here it will be 32 minus 5 plus 1, right? So it will be 28. So the output here that we're expecting is 28 by 28. And that's what we get here, a 28 by 28. Yes, this is what we call an activation map. If we call it an activation map, if we have an activation function added to it. Okay, so this is, or we can just call it as a feature map, okay? Okay, perfect. So that's what we know what we have. How about now if we have a second filter? We've seen that already. Now we're just gonna have another feature map here, and then we have, and so forth. And if we have many features, filters, for example here, if we have 6 filters, we're just gonna do the same. You see, we're just gonna do 6 filters. And you see how like the annotation in here, 6 filters, 3, we can call this like CN channels in. So 6 filters, 3 channels, 5 by 5, and then we get 6 output channels, 28 by 28. Okay, cool. Okay, so we've seen all that. Of course, we add bias to it. Every filter would have its own bias. So we add a bias to, with every filter, we add a bias. Okay. Now we can have more batches. So here we're talking about a single image. We can have many images, right? And so forth. And so the conclusion here, if we wanna like give, so we have n number of batches. For example, a batch would have 5 images, so our n would be 5. If it is an RGB, it will be 3. The height and width of that, okay? And then what's our Cout? Cout will be just the number of filters that we have. And then the Cn here is from our input, and then the width and the height of the kernel. And so now we can say just how before we said, oh, okay, well, this is what we're expecting, 28 came from 32 minus 32 minus 5 plus 1, then we can make a generalization of this. And we'll make that generalization of this now, and even when we'll add padding and Streisand and all that, there is an equation for that. Okay, so now if we stack convolution layers, perfect. So now I will ask a question. So if we stack, so okay, so now we have that, right? This is something, so now when we look at this, we should all be familiar with, oh, okay, we have this input. This is a 32 by 32 with 3 channels. Okay, it's an RGB. And when we look at this, we know what's going on here. 3 filter, 3 channels, 5 by 5. We're expecting this, and so forth, we can apply it. And this is what a CNN is. But the question now I would say is, can this is something all neural, so I'm going to step back and say all neural networks, they actually aim to do one thing. They aim for one thing. There is a theorem, a very popular, it's called the universal approximation theorem. And this is what deep learning, this is what neural networks is all about. What is this universal approximation theorem? It pretty much says that any function can be approximated with enough data and enough inputs, let's say, okay? So enough inputs, with enough inputs, we can approximate any function, okay? That's the goal. That's all our goal with all these architectures, even with the high non-dimensionality and all that. The goal is we're just trying to approximate functions to either classify different objects or to do regression or anything. But most of what we're working with is nonlinear, right? Most of the functions, if you want to really, you know, linear would just take you so much. So here I would ask you the question, if we just do this, is this, can really this mimic a nonlinear function? Meaning what? Meaning for us to actually to have some mapping nonlinear, meaning like we gotta have some nonlinearity inside. And really on convolution here so far, we're just multiplying and adding. There is no nonlinearity there. And this is where, this is why I wear my shirt. This is where real you comes, okay? So then that's real you, right? Real you have that linearity that you really introduce after every output. And that's how we get a nonlinear approximation that we're going for. Okay, and I hope that is very clear exactly. And this is what this slide shows. So we have the conv layer, we have our conv layer, and then we add our activation function here, which makes our output now nonlinear. And this is exactly what we're looking for. Okay, perfect. So this is okay. If we got so far here, we are in very good shape. Now, this is going to be like very easy. If I were to ask you this, if you have a 56 by 56, you can think of its image or whatever. Now, don't think of it as an image, because you're going to say, oh, well, how is that 64? Well, yes, the RGB, the input will be 3 images, but sometimes when we are in the middle layers, you can have something of like this size, for example. You can have something of here channels in 64. So this is CN, channels in 64. So if we have our channels 64 and 56 by 56, and I say we're going to do a 1-by-1 convolution with 32 filters. So let's pause there. A 1-by-1 convolution with 32 filters. What's the expected output size? I'll ask you then, every filter, how many channels does it have? For us to do the cross correlation, every filter has to have 64 channels in it, right? Okay, so what's the expected size? The expected size would just be 56, 56, 32, okay? 32, because now the number of filters became our channels out. Okay, So I'll pause here. Now we're going to talk about padding and stride and pooling. These are just spatial dimensions. You see, like how earlier they said that there was a good question, how like applying all the convolution definitely like shrinks the size, and you know, so padding now comes, and we're going to talk about all that. But I'll pause here, and we can take any questions. Elvis, if there is a question, please.
No, I didn't see any new questions, so.
Okay, perfect.
I think we can move forward.
Okay. So padding and stride and pooling. Exactly, because the outputs get shrinks very fast. For example, especially if we use kernels that are like, for example, here, for example, if we start by 32 by 32 and then we use a 5 by 5 kernel, after just one, okay, we're gonna get 28 by 28. And after a few layers, we even get 4 by 4. And because of this, we would like to introduce padding. So padding is just pads zeros to the outside of our input. Okay. And so, for example, if we have this 3 by 3 input here, we pad it by zeros all around there, and then we do our cross correlation. And then instead of before, if we did not have the padding, what would be the expected output? It would be just 2 by 2. But now we actually get a 4 by 4. Okay. So straightforward there. So now again, same way how we try to predict the output shape. The output shape now, we're just gonna add the padding to the height and the width. That's gonna be our output. And a very common choice, what's the padding size? It's the kernel minus 1. So for example, if our kernel is 3, a typical choice would be 3 minus 1 would be 2, meaning we're gonna pad 1 to the right and 1 to the left. If, for example, if our kernel is 5, what we'll do here is 5 minus 1, it's 4. So we're gonna just pad 2 to the left and 2 to the right. Okay. This is a good point here to say this is why when the kernel size is odd, it works well, because that way we can add even number of paddings to the right and to the left. But if the kernel size is even, when we do this and then we split by 2, one of the sides will actually have one more than the other. Okay, and the stride is kind of like we can think of it as the other way around. So you see how padding is actually, so we keep that dimension not to reduce as fast. Actually, stride sometimes maybe want to reduce the dimensions as fast. And this is what, for example, here when we use stride, and this is, for example, here what you can see is pretty much we just skip couple slides here. So for example, here a stride of 3 for the height and a stride of 2 for the width. So for example, we start here, right? So our kernel is overlaid here, we do the cross correlation here, but instead of sliding it just 1, we're gonna slide it 2. We're gonna slide it 2 for the width. So the next one actually will be here. Will there be another one? no, there will not be another one, because if we slide it another one, yes, we're gonna cover only one, but we're not gonna cover the other one. So for us, we have to, for this one to be calculated, the kernel has to cover everything. And here 3 for the height. So we actually, instead of actually going only down once, we're gonna actually go down 3 times. Okay. And then you can imagine how, like, doing it this way, it would really shrink our input size. Okay, and this is how we can change the spatial dimension, either like really growing them or really shrinking them on a hard pace. Even because, like, even a kernel, okay, just a kernel really shrinks them, but Stride does even more. Okay. Same way we try to do to say what's the output shape. This is what we had before, and then what we just do, we add now the stride to it. And these are, again, these are taken from the book. And we said that the typical choice would be just the kernel -1, and that's what we have here. This is a typical choice, right? Not always, but this is, and then if we replace this one on our equation, we're just going to get this one here and here. If the height and width are divisible by the strides, the output will just be the input over the stride. So for example, if we have an input of 8 by 8, and then we say the stride is 2, our output will just be 4 by 4. And the last thing is pooling. So pooling, there are 2 types of pooling. So pooling, again, when we talk about pooling is, and this is actually maybe even in interviews, or what is pooling? Or pooling is just downsampling. In one word, pooling is just downsampling. For example, here there are 2 main types of pooling. There is max pooling and there is average pooling, and all that it does, there is no convolution here or anything, but we have our window, and then we just take, so this is our window, for example, 2 by 2, and then we just take the max from it. Okay, that's our max pooling. So for example, here 4, and then we slide it, and then what's the max here? It's 5, and then so forth. The average, we'll just do the same, but it's just going to average them instead of taking the max. And you can see how it is downsampling. For example, here it's scaled down from 224 by 224 to 112 and 112. Okay, and then same thing here. Same thing here. So this is an example of max pooling, and this is an equivalent example of average pooling. Okay, so what we'll do, we'll go through the code, and then if there are any questions after the code, we'll take those questions, and the last thing that we'll cover will be the Linux architecture, and we're certainly ready for it after what we have covered so far. Okay, so let's now go back to the code and look at how padding and stride and pooling were implemented. Okay, and I will share. Okay. Okay, great. So padding first. So padding. So I hope everything now is everyone is following, maybe except those maybe even those initial equations, those were fine, but I think if you are lost at any point, we'll have some time at the end that you can ask. Okay, so apply 1 pixel padding on all sides. So this example of padding is applies 1 pixel padding on all sides. So let's see here. So we start with, okay, we have a reshape here. Okay, so we'll reshape it because we want to add, remember, the batch and the number of channels, okay? And we do our conv here, and then we'll reshape it here. Okay, so if we reshape it, if we're gonna just take out now the batch and the number of channels. So for instance, here we have our X is of size 8 by 8. And then when we apply this with, okay, so so this is what's key. So here, this is, so when we look at this here, what are we seeing? We're seeing that our kernel size is 3, meaning our height and width of the kernel is 3 by 3, and our padding here is 1. Okay. So meaning we padded our input by 1 to the right, 1 to the left, 1 above, and 1 at 1 below. So with that, when we run this, let's say if we do not have any padding, let's say if we do not have any padding, what's the expected output here? It would be like the 8 minus 3 plus 1. So we're expecting 6 by 6. But because we padded 1, now we're expecting, now it's the same. Okay, so really straightforward, right? But all this is really important for what we'll see next as we go. And then so when a kernel has different height and width, setting different padding numbers for height and width can make output have dimensions, same dimensions as the input. So here our kernel size, the height is different than the width. The height is 5 and the width is 3. And if we want to make the output the same as the input, then we can just pad 2 and 1. So these, the padding will also be different. Okay. The stride, we talked about how the stride, we would just, for example, here 2, and again, I'll pull up the stride here. You can see how the stride would just with here, so it's like it skips, right? It's by how much do we slide our window. And then here we have our padding to 1, and then our stride to 2. And then here we got 4 by 4. So how did we even get this 4 by 4? You can do the math, or you can, well, what did we say here? If it is divisible by the stride, for example, 8 by 8, yes, it is divisible by 2. So automatically the output shape will be just 4 by 4. Okay, and same thing here. We have a kernel size that has a different shape, and then here we can also pad with different numbers to the right and to the left. And this is what we do here. And even if our kernel is different, we are able to get the same. We are able to get a matching size on the height and the width because our padding is different. Lastly, for pooling, what did we say? Pooling, there is max pooling and average pooling, and this is what the book here they show. And pretty much we just take the same thing. It's going to be 2 for loops. Again, these are just implementations of the book, right? So this is not the, you know, usually you would just call this function, right? So you'd have just a for loop for your columns and a for loop for your rows, and then you would just take the max over, this is how you would just slide your window. And then you would just take the max if you're going for max pooling, and then you would just take the average or the mean if you're going for your average pooling. And for example, this example here, the 0, 1, 2, 3, 4, 5, this is exactly what they showed here. And then when you have a window, a pooling window of size 2, 2, right, you just go and you get your max pool, and this is what we get here for 5, 7, and then if we do the average, that's what we get. Okay, so right now, we covered all the main components of convolution and so forth. Here, this slide here, I'm gonna move now to this to showing that only. now we're ready actually to build our first architecture. And the book, they chose LeNet. So this is just like a summary of, you remember how we talked about the different sizes. So this is just a generalization of everything. So if we have our input, the numbers of channels in the height and the width, the hyperparameters, right? And this is your common settings, 3 by 3 kernel, 5 by 5 kernel, and 1 by 1 kernel, okay? The number of filters dictates the number of channels out. We have padding, we have stride. So this is our weight matrix, which will be, so see how this weight matrix now is channels out, channels in, the kernel height and width. So this is for this type of convolution. And then maybe we'll get to talk later. There are different types of convolution. For example, maybe one day you wanna say, you know what? Okay, I'm gonna pause here and maybe just, just step on the side and just say something maybe practical. Maybe you're gonna say, you know what? Okay, now you got the convolution very well, but maybe you wanna have a light. You want to have a light model. So what I mean is maybe you're doing deep learning on edge devices. If you're doing deep learning on edge devices, the weight matrix matters a lot. So if you can really reduce this and still be able to achieve the same performance, that'd be great. Okay? And there are other ways to do convolution that maybe we can see later. Or if you can look them up, for example, there is one called depth-wise convolution. And I'm sure because we have got so far until here, if you just go through that by yourself, you'll know exactly how depth-wise convolution is doing. And you can, for example, pick that, and then you can work it out. And then, for example, you can calculate the number of parameters, because this is the number of parameters, right? And then the more parameters you have, the more compute you need. So you can actually maybe compare, you can get the parameters from this one, and maybe you can get the parameters using this same convolution, but just it's slightly done differently, it's depth and then wise, and then maybe you can compare the two. So yeah, so there are different, but again, the core is the convolution, and then here the output size, we have the height and the width. And this is the general form of our output shape of the height and the width based on the input height, the kernel size, the padding, and the stride. And this is all between parentheses +1. Okay, so we got now to LeNet, and we're just going to talk about it, and then we're going to see its implementation that the book presented on the fashion MNIST. So here now, you see maybe before our today's session, maybe if you looked at this, you wouldn't know exactly what are all these numbers representing. But I hope by now you look at them and you know exactly what's going on. But there is a tricky kind of thing here. That this I just took it from the book, but there is something tricky for this with this image. But if you get it, you know very well that. So for example, here we have a 28 by 28 image. So if we apply, so if I tell you, you know what, I tell you we applied a 5 by 5 kernel. If I just tell you that we have a 28 by 28 image and we just applied a 5 by 5 kernel. What's our output? What are we expecting? What's the size of our output? It's not going to be 28 by 28, right? So there has to be something that we have done into this. And this is LeNet. So to answer that question, he padded. So he padded 2 to the right, 2 to the left, 2 to the right, and 2 all over. And that's how, for example, so the input really is 32 by 32. And then the kernel here is 5 by 5. So now when you actually 32 and with the kernel 5 by 5, 32 minus 5 plus 1, you get a 28. And then you have, how did we get again this 6 channels out? Meaning our kernel simply had 6 filters. So by the way, so Lunet architecture proposed in by Jan LeCun, I'm sure you all know him, Turing Award of last year or the year before. So the one of the first successful applications, because but then why it died? Why kind of like the CNNs, they kind of like they didn't keep the momentum, primarily because they needed a lot. You see, like how all this, they needed a lot of data to train on. And that's so a lot of data, and that's now what we have, a lot of data and also a lot of GPU power. And with all that, we can even do more high resolution images. We can even now, you know, how the billion parameters that all the new models really have. Okay, so now going and looking at this, we say, okay, by the way, so this is a single channel. We say, okay, we have a single channel, but our output has many channels. Okay, well, that's probably because we use many filters here. And then, you know, the size here. And then here we apply pooling. Back then, there wasn't, max pooling was not proposed. So it was just average pooling, and then you do another conv layer, and then you do pooling, and then here you just go from here to like dense layer. You just pretty much flatten this into a dense layer and so forth. And then here you have 3 fully connected layers. Okay, so so this is again how the book details it, and this is exactly what the architecture is. So we start with the image, exactly how we said. We have a conv layer of 5 by 5 size, the heap added 2 with 6 filters, and then we do average pooling. The pool side, the window size 2 by 2, the stride. And usually, this is a good point here to mention that usually the stride would be the same size as the pool window. So for example, here pool by 2 usually. And then here there is no padding. You see how here we padded. Here there is. Can you see? You can see my screen, right? Just want to make sure. Yes.
Yeah, we can see.
Okay, and so forth. And so right now, I feel we're all, and again, to make this, of course, to make all this, to make all this the non-linear, right? Because we're trying. So we have to add the sigmoid. So for example, now we're talking about real U. Back then, there was just sigmoid was the activation function. And this is how we go about it. Okay, so now let's go to the last part and just go over the code for this one. And so for this one, okay, so we're running this on Colab, and let's see. Okay, so I believe you can see my Colab window now, and I'll zoom in. Okay, so I believe you already, it's just sequential, so we're just putting layers sequentially. A convolutional layer, then we apply our sigmoid, then we apply an average pooling, then a convolution, then sigmoid, and so forth. And then here we specify the kernel size, the stride, and so forth. And lastly, here, after we flatten that, we just have to be fully connected layers. Okay. That's so here with the book, they say they just wanted to try this out with just a random input that's 28 by 28, and they just print out the different the structure. They just print out the network here, and this is exactly what we went through on the slide. Okay. So now to apply this on the fashion MNIST, we specify a batch size, a large batch size here, 256. Again, batch sizes, they're usually power of 2s, so you can 64, 256, and so forth. Okay, so once we load that, I believe you already maybe have done, if you have done this for MLP performance layer perceptrons, this will be just the same. So this is for our test. So this is eval is for our test, and then we'll have our training, and training will be down. And then here we're making sure that we're using our GPU. Okay, this is D12. So this is a function in that's probably just adding an accumulator there. And then here we're copying the data here to the GPU, and then we're just calculating the accuracy. So when are we going to call this? So we're going to call this function when we're going to evaluate the accuracy of our test set. Okay. So for training, we initialize our weights. I think somebody asked a question earlier. For instance, here we're initializing our weights using Xavier, and we specify that we're using our GPU, and then the optimizer is GD. The loss is cross entropy. We have an animator to show our results here at the bottom. That's what the animator, we have a timer, and then now we go and iterate through our number of our epochs, which we will specify later. We tell the model we're going to train. We zero out our gradients. We copy the data to the GPU. We predict our y-hat. We calculate the loss, and then we backpropagate, and then we update the step. And then we keep track of our training accuracy here, and then we keep track of our training accuracy there. And if this is for the animator, when are we going to plot that? Pretty much. And then here, the test accuracy, we go back and we use the evaluate accuracy GPU function that we declared up top. And these are just some printouts to print out. And then we just specify here the learning rate and the number of epochs, and then we'll retrain. And then it just trains. And pretty much now we have trained our model that it's predicting with an accuracy of 80%, say, on our first CNN network. And I will pause here, and we'll take questions and any discussions, anything specifically on the chapter that I may have skipped, maybe. Feel free to ask me, and anything I know, I'll share. Yeah.
Okay, just waiting for questions if anyone has. Sometimes it takes a little while for people to ask their question. But there was one question here. I think it was about the number of input filters. Okay, no, that's not the part. So they're talking about something about sizing. They say, I understand how stride padding affect the size of the output, but I'm not clear on how the filters change the output channels. Any idea on that?
Okay. So he's saying that he is clear on how the stride changes the output,
right?
But not quite on how that is affecting
how the filters change the output channels.
Yes. Okay. So the filters. So for example, we can go to any of these. So the filters, the number of filters is the number of our channel outputs. And okay, so to even explain that more, for example, here we have 2 filters, so we get 2 output channels. Okay, I mean, it's like we take one filter. It's like, think of it as like this one here, where, for example, this one here, we only have one filter, a filter that has 2 channels. So we only got one. Now, when we add another filter, we'll get another output channel. And then we can think that that's why a channel, right? A channel is related to a filter. That's why sometimes we can even relate channels to the features they're extracting. That's why we can really relate the feature, wherever the eyes on the high level, or maybe the edge detection on a lower level, we can relate them to the filters, but actually we can relate them to even the channels, to maybe the channel space. Actually, next time, there is something that I may have skipped here, which is a receptive field. And that can maybe help visualize this. I hope that.
Excellent. I think that was pretty clear. So another question, could you discuss additional applications of CNNs in addition to the visual space?
So yeah, you know, so CNN is like, for example, they can even be used as a 1D. So CNNs can be used even for text, if you would like. And so that's like 1D. And instead of just RGB, they can even be used with more than even 3 dimensions. So there are like, that's still visual, but it's visual, but there are more dimensions than just RGB. For example, so for example, the geospatial maps and all those, so those, they have like an extra dimension. So that's for besides visual. Also here's another way how you can, so here's, please guys, here's another way how I would like you to also think of CNNs. So think of CNNs not only for computer vision, but think of them also as feature extractors. Meaning what? Meaning, you see how we have this? Okay, we may extract something from wherever input we have. For example, that question that somebody just asked, something else than visual. Whatever you have here, for example, you may apply CNN, and then once you get here to the end, maybe your output is not necessarily computer vision. For example, you can feed this, so you can think of this as a feature map that you can feed it to other networks. You can maybe feed this into LSTMs, for example. You can feed this into the different things. So yes, they are used for computer vision, but they're also, you can think of them as feature extractors, and then you may want to use those features on other things. Okay? And all those are very good questions.
Yeah, they're very good. Everyone is so curious about the CNNs. There's another one, I think, another question here. So it says, stride, pulling, kernel always reduce size, and padding always increases size, but filters can either increase or decrease depending on our choice. Is that the right assumption?
So that's another good point. So you see, so here is you see, the deeper we go, what do you notice? The deeper you go, you notice that the dimensions really, the size gets smaller, but the channels, which are the filters, the channels out get larger. And this is just kind of like best practice, what has been found to work best. We're like kind of like sacrificing that spatial dimension, right? Because we're making smaller, but we're actually getting more features from it. And you can think of now those channels out. So for example, here, let's say, for example, here we have 4, right? We're looking at this one, here we have 4. So you can think now maybe all this more, like for example, here maybe we have 8 or 16. Each one of them maybe is getting like, so maybe this one here is kind of like representing the eye. This is intuitively, because really they're not independent like that. They're all in a way related to each other, but we can think of them like that. So we are sacrificing, we are making them smaller, but for us to make them smaller, we have to also keep some of that feature information, and that's how we do by increasing the filters, which is the channels out. Yeah.
Okay, cool. I don't see any other, just some other comments there, but no questions. Anyone else has any questions to ask? I think you finished your presentation, right, Salim?
Yes. This is it. And again, so actually, this is now the basics. And now that we all can look at this one, and then we all got it. I believe now just taking this now to a next level, and from AlexNet to the latest ones, we're all going to be very comfortable with it. All that I would say is these equations. If you have, I'm gonna check the Slack, the Dyer Slack channel. If you have still any doubts about this, please let me know. I will share maybe like a diagram or something of here, how like we went, how we had like here 4 indices, and the 4 indices were really, it doesn't really, this translation invariance, how it's not, these are intuitions behind CNNs. This is how we went from all that the number of a huge weight matrix to a much smaller now weight matrix, which we call the kernel.
Yeah, everyone is so happy about the presentations. They really loved it, apparently.
Well, I'm sure that now it's going to be even more fun, right? Because now that we understand all this, now you can go and, well, what I would suggest, I know, for example, I went very fast through this. So what I would suggest, go back through this, at least maybe now start changing maybe small things. Okay, we said this is sigmoid. Okay, now we know that RealU works better than sigmoid, right? Start changing things like that. Okay, here they used average pooling. Okay, do max pooling, and now you have enough. Now you have enough to start building things, and I believe the even more passion would come when you actually build something and you can share it with friends and others. And so, for example, for this, actually, I'm going to wrap up with this. So what I would wrap up is my experience with deep learning, with machine learning, and then, you know, I'm no expert. We're always still learning all the time, but you get to realize that yes, deep learning machine learning is important, but if it doesn't make it to production, if others don't use your application, you know, so what I would say, but it doesn't have to be complex. It can be just something like this. And there are tools, for example, I really like this tool called Streamlit, which you can just easily build an app for it, a web app or something. So just use just tools like this, where you can just build something and you can just post it and things like that. And yeah, so that's what I would say.
Cool, thanks, Salim. And that's a great suggestion. Again, towards the end, someone actually asked in our previous session whether, you know, if anyone was interested in doing a presentation on using Streamlit to do very basic demo or something like that. I think that would be great. And if somebody really, like you said, you are encouraging people to try it, I think that's a good challenge. And if someone gets to do it, I think that would be a great presentation. I think as a project, that would be awesome. We're going to have a project towards the end of the whole program. So I think that would be a great time to think about it and to start to do some investigation there. So thanks for that suggestion.
To add to that, Elvis, even, and this is like even personally with like colleagues and all that, even like, I don't know if anybody's looking for jobs or not, but when you are looking for jobs and you go and you even say that, hey, okay, I built this, even if it's not too complex, but I built a Streamlit app for it, or just whatever app. Like for example, back we used to use Flask, but now I feel like Streamlit is even more friendlier and all that. You can just use that, and that's perfect. You may even pull it up on your phone and be like, hey, here it is. And once you have even your Streamlit on an app, you can even put it on a Docker image, and then you can start playing. So I think so. This is kind of like so yes, deep learning and machine learning and all. But yeah, but just share with friends, share with others. Yeah. Okay.
Cool. Thank you. Thank you very much, Salim.
Yeah. See you guys next week.
Thank you. Bye.
Okay, bye.